our next law is Lenz's law. It is not one of Maxwell's equations, but it is related to one of Maxwell's equations. So it says, my phrasing, that induced currents create magnetic fields that oppose the d phi b dt that, and the wording here is critical, created the induced current in the first place. That may sound like a circular definition, but I told you the magnetic field is loopy, so there you go. Induced current. So what this means, you have a B field changing inside of, say, a metal loop, and you're going to make a current. So that's the EMF. The EMF over R is the induced current. But then, of course, that current will make its own field. So we're just thinking about what kind of a magnetic field does it make. And this is basically a rule about which way the current will go. And there's another way you can state Lenz's law. Here's another way to state it. The EMF is minus d phi b dt. You can write that. You can write Faraday's law, and you can say this. Lenz's law is just the fact that there's a negative sign there. It's just a way to keep up with that. I imagine that Lenz ran around in the 19th century and kept telling people, you know, there's a negative sign there, and reminding them, don't forget, there's a negative sign there. And my theory is that they just kind of got sick of him and said, we'll name it after you if you'll stop reminding us. Okay? So that's not really, I don't think that's what happened. But that's how I imagine it. And what we're going to do now is show you how it's useful. Lenz's law is actually extremely useful in a lot of situations. We'll go through a few of those.